This is a preview for the exam for upcoming week for Financial Modeling 6207. The exam will cover questions for pivot table and questions for portfolio model. For pivot table, you can refer to the material that we cover in week 1 and also the take-home exercise. And shift your main attention to question 2. That's my suggestion. So it counts for 90%. So these will cover chapter 8 to 12. Now we don't need to review for chapter 11 since we do not cover it. Chapter 11 is just a chapter for calculating beta, and I believe we have a lot of those exercises in our previous classes, like classes of investment and financial management. Now the exam will take place in class. You need to look at the questions in PDF, work on the model in Excel, provide your answer to Canvas. Now I can make some suggestions here. I would suggest you to first work on your model in Excel, complete it, and then start to answer questions on Canvas. So after you have calculated, for example, global minimum variance portfolio, variance and covariance matrix, and then you have calculated the efficient frontier, then you can work very smoothly to all the questions on Canvas. The exam is open book, open note. You are free to check previous exercises and also slides, homework, take-home exercise, and also videos. However, the exam should be your individual work. There shouldn't be any collaborations between your cohort. To start the review, I will mainly focus on the portfolio maximization part, and I believe you can easily go through the materials related to pivot table. Now, for portfolio optimization, we first learned a couple of chapters to get used to matrix calculation. Matrix calculation in Excel can be very straightforward and much easier than calculating everything manually. So Excel, you have different cells and those are spreadsheets, and it matches perfectly to the expression of matrix. So we just need to learn a couple of tricks or a couple of functions related to the matrix calculation. For example, matrix multiplication. These are the functions, and M inverse, transpose, and there are also some user-defined function, unique row vector, and unique column vector. So I want to make one specific note here. Matrix multiplication will only work for 2 variables, x and y. If you want to calculate xy times z, you need to first do matrix multiplication of these 2 first, and then add one more matrix multiplication to calculate the product or the multiplication between x, y, and z. For matrix multiplication, the order really matters. Okay, so for matrix, x times y does not equals to y times x. So that's why we have to use the matrix multiplication in this way. So using double matrix multiplication to calculate the multiplication of 3 variables. So then we move on to portfolio basics. So this is related to chapter 8. Here in chapter 8, we're doing some basic calculation for portfolios. So you'll learn how to calculate portfolio return and variance and standard deviation for 2 assets. We also extended for calculating n asset portfolios, the return standard deviation for portfolio of n asset. And for portfolio of n assets, we need to come up with the variance covariance matrix. So we're going to have a matrix, we call it matrix S, equals to the variance of 1, 1, and the covariance between 1 and 2, and the covariance between 1 and 3, and all the way to covariance between 1 and n. And the next row is the covariance between 2 and 1. Here is the covariance between 2, 2. Another name of it is the variance of asset 2. Here, 2, 3. In the third row, 3, 1, 3, 2, 3, 3. This is the variance. So all the way down, we have N1 here, N2, N3, and N. So this is also a variance. And you're going to see that these two are the same. Here, these two are the same. These two are the same. And this matrix is symmetric. Okay, so sigma 1 n, the covariance between asset 1 and n equals to the covariance between asset n and 1. And this diagonal part is the variance. That's why we call this variance and covariance matrix. And we learned how to calculate this using two methods. One is using a process. So S equals to some formula. We'll need to utilize a matrix called A, and A is just the excess return. So the return Ri minus R bar. R bar represents the average return. So method 2 will use variance, covariance, VBA code. So there are two methods here. And similar here for correlation matrix, we can also use a VBA or user-defined function to calculate the correlation matrix. And the input, therefore, for this is just the return of how many assets that you are considering. And then we move on. So now that we have returns, variance, covariance matrix of n asset, we can further calculate the efficient portfolio. Our ultimate goal is to calculate the efficient frontier. So to solve for efficient portfolios, so efficient portfolio should be a portfolio based on these n different assets. So we can manually come up with some combination of these n assets with some weight. So X represents the weight, X1, X2, Xn. We can manually come up with all these weights, but those portfolios will not be optimized. So to solve for optimize, we have to solve for the tangency portfolio given by a certain number of constants. I'm going to show you later. So to solve for one efficient portfolio, and then further to solve for another efficient portfolio using efficient portfolio X and efficient portfolio Y, we can efficiently calculate the efficient frontier. Now, this is given by two propositions, by the portfolio theory. So one assumption here is there's no other constraint, for example, short selling constraint. Now, what if there is short selling constraint? Now, one solution offered by Excel is we can use this solver. So solver will solve the maximization problem. Using solver, we can solve for the efficient portfolio for just one efficient portfolio. We need more efficient portfolios to come up with a frontier. To do that, you can utilize the VBA code to call Excel running this solver for a lot of times. So save some of your work to repeating the process. So now I want to explain the proposition or the solution of envelope portfolios. We call this envelope portfolios because efficient portfolios are portfolios that is above the minimum variance portfolio. So for the portfolios here, if it's above the minimum variance portfolio, they are efficient. If it's lower, they are envelope portfolio but not efficient. So this solution will give you a portfolio that lines on this curve, but will not guarantee that it will be some portfolio that above this minimum variance portfolio. So to get the efficient frontier, we need to first solve for different envelope portfolios and then have an idea of the minimum variance portfolio. And we can therefore calculate or know these portfolio above the minimum variance will be efficient. So then looking at proposition 1 and 2, these two together gives us an idea or a process to solve for efficient or envelope portfolios. Proposition 1 will already give us a solution. Okay, we can basically use solver to solve this multiple times and come up with different envelope portfolios. But with proposition 2, okay, we therefore, because based on proposition 2, we can use data table, save a lot of our work. Because as long as we know portfolio Y and portfolio X, we will know all other portfolios. All other portfolios, for example, portfolio Z, W, Y, they will be a convex combination of X and Y. So there's just no need for further calculating Z, W, and Y. And I believe we have an exercise showing that, okay, showing that we have a portfolio Z and we follow proposition 1 to solve for X, Y, and Z. And later we're going to find that for Z, they are all a function of X and Y. So going back to proposition 1, this gives us a solution. So these X solved by the formula here, this is the optimized weight. So we'll have a numerator S inverse times average return for the asset and some given constant. So this is the sum. So here the sum is just to make sure, okay, this sum is just to make sure that the sum of X equals to 1. So it's one way to guarantee that we have this satisfying. And the numerator will guarantee that we have a tangency portfolio. Now, how do our previous economists solve for this X? How do they set up the model? So they set up the model in this way. So they're going to maximize the theta. So theta represents return per risk, right? So this is the return and this is the risk. So theta here represents the return per risk. So the investor demand this type of return for every unit of risk that they are bearing. So we want to maximize this theta so that we can maximize this risk and reward, so that we can maximize the reward to risk ratio. And this is our objective function, and this is our constraint. Constraint is the X. So X is given by here. So the average return, average portfolio return is a function of X and individual return. Now we want the X, the sum of all these X, the X is weight, the sum of all the weights equals to 1. And the sigma is also a function of X and the variance covariance matrix, the structure or how all of these X's correlates with each other. So therefore, to solve for everything here, the objective function and then the constraint here, the economists, they solve this. So X equals to S inverse E R minus C and sum of numerator. These are all possible combinations of n different assets. So we're gonna connect them here and connect them here. Okay, so each of them will have a theta. Let's say theta 1, theta 2. And this is theta 3. So theta here will be the slope. So it will be the slope here. So R minus C divided by sigma. So it will be the slope of this straight line. So now here we're gonna easily see that theta 3 is greater than theta 2, greater than theta 1. So the max will be theta 3, given this level of constant. So therefore, we cannot find any other combination given this level of C. We cannot find any other combination of risk and return or portfolios, a combination of different N assets that yields a larger theta than theta 3. If there is one, theta 4, there wouldn't be any feasible strategy here. Therefore, that will only solve for one single envelope portfolio. Okay, so that's for a given C. Now we can change the C. The current C is here, and we can have a new C, and its tangency portfolio will be here. So therefore, we'll find a portfolio. Let's say this is portfolio 1, and we'll find portfolio 2. Okay, and we can have another C here, and the tangency portfolio is here. We say P3. If we change this constant C multiple times, then we'll have multiple different envelope portfolio lying on the edge of this frontier. So then we can plot them and maybe connect them. You're going to see a frontier like this. And the portfolio lying on this frontier, they are all optimized portfolio. And then we can find one portfolio that has the minimum variance. In this case, minimum sigma, that's the same. So sigma minimum. And all of those portfolio that's above this minimum variance portfolio, those will be efficient portfolio. Below, those will be envelope, but not efficient portfolio. So therefore, the idea is we need to change C. So if we have different numbers of C, we'll get different envelope portfolios. Then we'll have this shape. We can make the graph look like this. So that's for proposition 1. So let's see how to implement it in Excel. Now for proposition 1, we can basically write this in Excel by just using one formula. Now the formula here is a little bit complicated. So here is nothing but just repeating the order here. So repeating, so now we first need to look at the numerator. So we will need to use S inverse. So we're gonna first inverse here, and outside of this inverse, we need to add matrix multiplication. So multiply S inverse by the difference of return and the constant. So here, just calculate the difference of return and constant. So that's will be the numerator, and the denominator will be here. We're summing, okay, doing a sum of the numerator. So we're gonna have here everything show in one column. So this will be a column vector. Okay, this will be a column vector. So these will be the X. So Xi. And we can use the portfolio weight here times the portfolio return. So times these are the asset return. So use asset weight times asset return. So this will be a weighted average. So this weight is here, return is here. Here it shows you that you can basically use the weighted average method or use the matrix method. Those are the same. So you can use sum product or you can use matrix multiplication. But you need to first transpose the X and times return here. Simply because this is expressed in one column. Okay, we need to transpose the X. And for calculating portfolio standard deviation, it's just also given by the formula. we need to do X transpose times S and times X again. So sigma equals to square root of X transpose times S times X. So if we vary in the C, we're going to have a frontier like this. Okay, there is a process you do data table, and I mentioned proposition 2 allows us using data table to generate this efficient frontier. Now, going to the last part of this portfolio model, we learn how to add constraints to the portfolio maximization problem. If we want to add constraint here, restricting investors not to have any short selling activities, so that means X should be greater than 0. If X is negative, we're saying that we're borrowing money, so borrowing money from X. Another way of understanding it is we are short selling X. So you're selling X. So if X is greater than 0, we're just saying you're buying, okay, or selling. If it's negative, it's selling. So we don't want any short selling here, then we need to restrict at one more constraint here. So X is greater or equals to 0. Okay, there is now, if you learn how to use solver, there's some easy way of solving this problem. You don't need to mathematically derive it. Excel is a computer. It can compute this for you. So here, since we have this constraint and we already talked about it, how to calculate efficient frontier without short selling. So we're going to use solver in Excel. Okay, you can refer back to the previous lectures and also some videos showing you how to use solver. We can also come up with different efficient portfolio, different envelope portfolios by changing the C. The idea here is, okay, we do not use data table because we cannot use data table. Now, in this case, we're adding some more constraint. The proposition 2 and proposition 1 does not work. So then, but to set up this model, to set up this theoretical model, solver can still help us do that. So we'll then just ask solver to do the hard work. So to change different constant. So if you do this a lot of times, you can come up with some frontier. So ask solver to do this repeated task. Now, we can manually use solver to calculate one envelope portfolio, but we don't want to do it for 100 times, 50 times, just manually. So you can use the VBA code that provided in this class, and you can solve the efficient frontier by just one click. So then we can put in everything together, summarize what Markowitz portfolio optimization model says. Its portfolio optimization problem says that, okay, there is a framework to find the optimal portfolios, and the optimal portfolios will offer the best risk and return opportunities or best risk and return combinations. Say you already have some individual assets in your portfolio. So how to optimize the portfolio weight. This is very remarkable. Before we know this portfolio theory, people will only know that, okay, do not put everything in one basket. And people know the idea of diversification, but there's no theory to quantify the relation between risk and return. Now, portfolio theory comes and shows people that there is a way to mathematically solve for the optimized weight. And the different combination of different combination of risk and return, and also solving for the optimized weight, we can come up with an efficient frontier. Okay, on this efficient frontier, from here, they offer the highest return given one level of risk, and they offer the lowest risk given one level of return. Within this efficient frontier, there's a global minimum variance portfolio. So its variance is lowest here, so lowest variance. And only portfolios that is above this minimum variance portfolios are efficient. Next, portfolio optimization theory says that the way of searching for optimal portfolios is to looking for the portfolios offers the highest Sharpe ratio given a certain constant. So after you have a frontier, you know what's the best possible portfolio that you can invest. Now there will be an individual's choice to mix between optimal risky portfolio P and the T-bills and the risk-free asset. Everyone can invest differently, so they can allocate their assets differently amongst optimal risky portfolio and the risk-free asset. Everyone will invest in P regardless of their degree in risk aversion. Their risk aversion level will only change the proportion that they invest in optimal risky portfolio and the risk-free asset. The choice of the portfolio and the determination of proportion that you want to invest in risk-free versus risky portfolio are two different decisions. This determination of optimal risky portfolio is purely technical, saying that we need to first come up with an efficient frontier. And then there's a risk-free asset here, and then we can just find the tangency portfolio. These are all technical. It will be solved mathematically. But the choice that you made on, how much proportion you want to invest on the portfolio P, the optimal risky portfolio, determines the location that you are in on this straight line. And this is very personal decision, depends on your preference, and also your utility function. So your utility function should reflect your preference. This graph will show the idea that the optimal risky portfolio here offers the highest Sharpe ratio and also has the steepest slope. Okay, finally, these are some important formulas. So some of you may, when you're entering your formula in Excel, sometimes you will get lost about, what's going on there, how to understand those Excel formulas. I think all of those Excel formulas are related to the formulas showed here. So these are nothing but calculating returns and variance. And the idea of calculating return and variance are all here. Why we are calculating return in this way and why we are calculating variance in this way, these are mathematical questions. Okay, so that will conclude the review for exam 1.